Well, we've been looking through a new topic called Laplace transforms. And we've defined a Laplace transform, we've motivated the idea through differential equations, and we've calculated a few of these transforms using tables, using the definition, and also using the first shifting theorem. In this presentation, we're going to take the next step to the second shifting theorem. Now, I did promise I would revisit the example that I looked at the end of last class. Okay, I'll save that till the end. I wasn't quite happy with the wording of that question, so I actually slightly adjusted it. But if we have time, we will look at that at the end. Okay? Okay, so just to refresh our memory, a Laplace transform is just an integral transform. You take your function of t, multiply it by this exponential, and form this improper integral. Generally, lowercase letters represent functions of t, uppercase letters represent their transform. So little f of t, big F of s would represent its transform. And it's in the form of an improper integral. Now here's a table that we've been working from. This is slightly larger than the table you'll get in your exam. So please, before the examination, have a look at the table in the exam and see exactly what's there.
Chris, when you say it's large, the stuff that we're unlikely to, there's not something we have to learn from this table that will really stuff that's superfluous.
Correct. Yeah. Right. Yeah. Okay. So the subject of this particular presentation is basically this line here. Okay, so it will be given to you in a table, I'm sure of that, so you don't necessarily need to remember the second shifting theorem, but you need to know how to apply it. Now, as you can see, in this line here, you've got a Heaviside step function multiplying by some other shifted function, and it's claimed that its Laplace transform is over here. Okay, so just to refresh our memory, the Heaviside step function, also called the unit step function, is something like this. Okay, so it's 0 to the left of the jump point, it's 1 to the right of the jump point, and at the jump point, it's sort of half the jump, so it's 1/2. Now, different people, different textbooks define the value at the jump point in different ways. Okay, irrespective of whether you define it or not at the jump point, it doesn't affect the transforms, okay? Because it's just a point, it's just a single point. Okay, and then you can shift your Heaviside step function, say a units to the right, and it's, you know, basically the jump happens at t equals a. Okay, so the second shifting theorem. Now, I've put a little g and a big G here just to make it consistent with what's in the table. I think originally I had these notes with little f and big F, something like that. So if you want to adjust them, please feel free. Okay, so let's have a look at it. Suppose I have a function of t, little g of t, and it has a Laplace transform big G of s. In other words, this is what we mean. Then, the shifted function of the product, the Heaviside function with g of t minus a has this Laplace transform. Okay? Now, remember, this is just a function that switches on and off. So if I combine the Heaviside step function with multiplication of some other function, you're going to get some switching on at t equals a. So if I wanted to write this out in the sort of longhand form, well, for t less than a, this coefficient, if you like, is 0. So it'll be 0 times 0, 0 times g, sorry. At the jump point, this is 1/2. And, well, if t equals a, I'll get g of 0 here. And for t to the right of a, this is now fully switched on, so to 1, so it'll be 1 times g of t minus a. Now, hopefully you can see that what's driving the transform of this form is actually the transform of little g of t. Okay, so if you're given this form, you calculate little g of t, you just write down little g of t, calculate its transform, and then multiply by an exponential. So why is that true? Let me give you a quick proof. Okay, for this I'm just going to use the definition of our Laplace transform, the improper integral definition. Okay, so I can set up my improper integral. So that multiplies by whatever's in here. So I get something like this. And now all I really want to do is simplify. This is going to be 0 sometimes, it's going to be 1 other times, and at one point it's going to be 1/2. So if I split it up, split the integration up, say from 0 to a, and then from a off to infinity. In fact, I can split it up in the following way. From 0 to a, this is 0. So if I multiply everything through by 0, I'll just get the following. Now at the point a, so if I integrate from a to a, this is 1/2. So essentially I'm just integrating the following. So what will that be? That'll be 0, will it? And then yep. And then let's just worry about t, say, greater than a. Well, this now becomes 1. Okay? So if I integrate over a point, that's definitely 0. That's 0. So I end up with this. Okay? So now what I can do is make a substitution. What I would like to do is get rid of that t minus a and form some other new variable. So let's just say, I don't know, let q equal t minus a or something. So a to infinity. Thank you. How's that? All right. So we integrate from a to infinity, and a to infinity. Thank you. All right, so if we just sort of replace this t minus a variable with, say, q, well, dq is just dt. And working with the limits of integration, when t equals a, q is going to be 0, and as t approaches infinity, so's q. So I can form the following. So I just replace t with q plus a. No, it's 0 because I've made the substitution. Okay? So when t equals a, q is going to be 0. You with me? Yep. Okay, so now what I can do is pull out one of these exponentials. Okay. And you'll see that's just the Fourier, the Laplace transform of g, and I've got this multiplication of this exponential. Okay? So that's why it works. So as you can see, it's just splitting up the integral into the components of, well, where is the step function 0, where is it 1, and where is it 1/2. That's all it is. It's nothing fancy. And they're just making a change of variables. Okay, so of course, we're going to be more interested in the applications of this theorem. How do we use it? Okay, it's nice to see why it works, but sometimes it's even more interesting to see, of course, how it works. All right, so here's a standard question. Determine the Laplace transform of this function. So we want to apply our shifting theorem. So in this case, this is just g of t minus 4 equals t minus 4. So if g of t minus 4 equals t minus 4, what's g of t? T, right. Okay. So whatever's in here is exactly here. So if I replace this with t, I replace this with t. So g of t equals t. Well, we want some sort of form like this. Well, a would be 4 in this case, and g of t minus 4 is just t minus 4. So I construct g of t. Okay. So all I need to do is to apply the theorem is calculate the Laplace transform of my particular little g, and then multiply it through by an exponential. Okay? So you can see a method here. Identify that you have the form that you want. Find little g of t minus 4, some shifted g. Identify your a and identify little g of t, because you need to take the transform of it. So by the second shifting theorem, we have this. Okay, so for our problem, the Laplace transform of little g is just the Laplace transform of t. So I'm sure some of you can remember the Laplace transform of t. If not, just go to your table. I find a t there, so the Laplace transform is 1 on s squared. So we use this and this. By the second shifting theorem, the Laplace transform of this is just this times e to the minus 4s. Okay, so hopefully you can see a little pattern kind of emerging. What's driving it is the function little g, okay, little g of t. Identify it early and take the transform. Then just multiply through by a suitable exponential. Questions? Okay, so that's a pretty basic one, but hopefully it's given you a little taste of of the ideas. Okay, here's one going the other way. Now I think I've changed H. In yours it might be big F. That's okay. You can keep it as big F as long as it's not, I guess, big G. That's probably not the best notation. Now, of course, the second shifting theorem goes the other way. If I have some sort of function of S like this, and I want to calculate the inverse, I can go up here. Okay, so the inverse transform of this must be of this form. Okay, so this is an example where you want to use the second shifting theorem the other way around. So you start with this and you want to form this. Okay, so how do I do that? Well, you identify your A and your big G of S, calculate the inverse transform of big G of S, and then shift it and form this product here. Now, we're going to have to use two techniques for this one because I'm just going to split it up. Now, the Laplace transform and its inverse are linear operators. So for this one, I'm just going to break it up into the following form. Okay? I can get the first inverse transform from the table, and then in the second inverse transform, I'm going to use a second shifting theorem. Okay, so the inverse transform of 1 on S squared is just t. So the interest here lies with this inverse transform. Okay, so let's consider the following form. So essentially I want to build that from that. So A would be positive 2, and big G of S would be 1 on S squared. Okay, so by the second shifting theorem, what we want to do is take the inverse transform of that. The inverse transform of that to form little g of t, and then shift it, and then multiply through by the appropriate Heaviside function. Okay, so the inverse transform of 1 on S squared, that's just t, again, just from the table above, or just from above. So let's shift it. So A is 2. If G of t is t, then G of t minus 2, I'll just replace t with t minus 2. Say in brackets. Okay, so by the second shifting theorem, we have this. Thus, for our problem, this is just u of t minus 2 times t minus 2. So let's put our parts together. We've just calculated this inverse transform. It's that. Let's add in the two terms, and we'll get something like this. Okay? All right, so we've used the second shifting theorem the other way now, and it was part of a slightly more elaborate example. But what have we actually calculated here? Well, it's some function of t, but let's actually see if we can maybe sketch it and shed some more light on the situation. Okay, well, I'll just see if I can squeeze a little sketch in down here. All right, well, for t less than 2, what's this going to be? The whole thing? 0, right? And for t greater than 2, this is going to be... So I'm going to have something like the following. Okay, the point of interest is 2. To the left of 2, this is just 0. So I'll get that. Okay, to the right of 2, this switches on. So this will become 1. So it's t minus 2. So that's just a constant. Now at t equals 1, this is going to be a half. And if you plug in, sorry, at t equals 2, this is going to be a half. And if you work out the calculations, you get 2 as well. So this is the kind of curve that you get for the inverse transform. Okay? This sort of ramp loading type curve. Okay, so for t greater than or equal to 0, this is just the graph of what we've computed. Sorry, h of s. Okay? So notice that that question wasn't all about the second shifting theorem. There were other things to do, other calculations to do. So this is quite common in the sense that you need to be able to build the second shifting theorem and the first shifting theorem into your arguments for possibly more complicated problems. Okay. All right, determine the inverse Laplace transform of this particular function. Determine the Laplace transform of this function, right? So you can see that it's of this form with a equals 4 and g of t minus a equals t minus 4 all squared. So what would little g of t be for our example? If this is g of t minus 4, what will g of t be? T squared, right? T squared. So let's identify little g of t. Let's take its transform and then multiply through by the exponential function. Okay, so you can think of this as the following. A equals 4. So if I just replace t minus 4 in brackets here with t, I'll get t squared. All right, so we've got that. What we want to do is calculate the transform of g of t and then multiply through by the exponential function. Okay, so t squared, the Laplace transform of t squared? Well, I'm sure you can probably remember it, but all you need to go is over here with m equals 2. So you're going to get 2 factorial on s to the power 3. So 2 factorial is just 2. By the second shifting theorem, the Laplace transform is just this. So we have it's going to be e to the minus 4s times 2 on s cubed. Okay, so sometimes it looks easy when I do it, but students still have a problem with the algebra. They don't really understand shifted functions. And, you know, it takes them a while to go from g of t minus 4 equals something to working out what g of t is, little g. Any questions for that one? Okay. All right, determine the Laplace transform of this product. So again, let's try to apply the second shifting theorem. So it's in the form that we like. We would expect a to be positive 2 pi. G of t minus 2 pi to be this. So what would little g of t be? Sine t. Sine t. Okay, so this is what's driving it now, this bottom line. Let's take the transform of sine of t and then multiply it through by an appropriate exponential function. Okay, the Laplace transform of sine of t, well, go down here. With b equals 1, I get that. So the Laplace transforms 1 on s squared plus 1 squared. Okay. So by the second shifting theorem, the Laplace transform of this product is this. So for our particular example, it's just this times e to the minus 2 pi s. Okay, any questions for that one? You can see that what I'm trying to do is make it very clear how I've calculated certain transforms and their inverse. Okay, if I'm using a table, then I'm saying so. Okay? Now this one's a little bit more work. The examples that I've presented so far are pretty straightforward. This one's slightly harder. Now just check that, I think I had 5 on 2 here instead of 2. So just check that you've got what I've got. It should be 2. No 5 on. Okay. let's sketch this function, give it some graphical meaning, and then what we're going to do is actually use the Heaviside step function to describe this the f of t. Then we're going to use the second shifting theorem. And this is common for slightly more elaborate questions. You're not given the nice form to start with. You've got to come up with it. Okay? So this relies on a good knowledge of the Heaviside step function. That's why we spent a good part of the lecture looking at that. Okay, so what I like to do with these ones is just draw them first, draw the graph. So here I'm only interested in the case where t is non-negative. So what I'm going to do is just consider each sort of piece of the function separately. So for t between 0 and 4, the f of t is just the t function. At t equals 4, the value of that function is defined to be positive 2. And then for t greater than 4, the function drops down to 0. Okay? So, you can see what happens with the graph. Initially, you've got this function of t, and then it gets switched off. So what we're going to do is form some sort of representation involving the step function at t equals 4. Okay, so the question is, how do we describe the f of t in terms of a step function? Anyone want to? No, you went. What is it?
T minus u of t minus 4 times t.
That's exactly right. Good. I thought you were kind of volunteering him, like, no. And I'm like, no, I'll ask you instead. No, that's good. Essentially, just break it down to what happens before the jump and what happens after the jump. So, to the left, it's just the regular t function. Now, to the right, that t function has got to get turned off. So, what I can do is multiply exactly what I have there by the step function and take this away from t. So let's just verify that actually this gives us what we want. To the left of 4, this disappears. So it's just this function. To the right of 4, this u of t minus 4 turns on. So it's 1. So to the right of 4, it's t minus t times 1, 0. At t equals 4, we get half the jump. This will be 1/2. So you get 4 minus 2, which is just 2. So it covers every part of that curve, that definition. Okay? Now, this still isn't quite what we want, because we want, if we're going to use our second shifting theorem, we want it to be something like this form. Okay, we don't quite have that. But what I can do is do a little bit of algebra and sort of insert a term and take a term away involving u of t minus 4. Okay? So if I do the following, let's just, what I would like here is something like t minus 4 times the step function. So let's sort of insert something and take something away. Okay, so I'm going to team those up. Okay? So if I just re-bracket, I get that. Now, I can calculate the transform of the middle term using the second shifting theorem. I can calculate the transform of the first term just from a table. And I can calculate the transform of the third term from a table. Okay? So a little bit of algebraic manipulation can put it into a nice form that's suitable, at least for part of it, for the second shifting theorem. Okay, so for this you use a table. For this you would use the second shifting theorem, and for this you would also use a table. Okay? SST. You obtain the following. Well, the transform of the first term is going to be something like 1 on s squared. If you apply the second shifting theorem to that, you'll get the following. And if you calculate this from the table, you come up with the following. Oh, yeah, it should be. A will be, yes, minus 4s. Thank you. Okay, so that's another good question because it involves a lot of different skills in the sense that you've got to have some visual skills, get some good geometric understanding of the problem by sketching its curve, have some algebraic skills to rewrite the problem in a suitable form, and then be able to use the second shifting theorem and the table. Now, can anyone see another way of doing this problem without the second shifting theorem? Have a look down the table. Okay, I want to take the transform of that. Can anyone see a way to do it without using the table? Oh, sorry, without using the second shifting theorem? Well, this line here, t times a function of t. Well, if I factorise that t, I've got t times 1 minus the step function. So you could actually compute the transform of this, then differentiate it and plug a minus sign out the front. Okay? So what does this tell you? It tells you that there's more than one way of doing these problems. Okay? And you should be aware of shortcuts if you can. Now, I can't guarantee you that you won't get a question saying, use this theorem to show this, use that theorem to show that. Okay? But it's good to know shortcuts.